Hello everyone, this is our physics video. This is going to be our sort of catch-up video or summary video of the lessons that you did with Matthew. It's also going to be our chance to go through some of the work that's in the physics booklets that you were handed out in the school. So let's start there. With Matthew, we've already discussed a lot of these concepts, so I'm going to move pretty quickly. If you'd like a deeper dive on these ideas, then please review the videos from Matthew, those physics video lessons 1 through 7. All right, so things we've already discussed we've discussed the idea of distance, displacement, position, and position, I guess. So distance is the total distance traveled versus displacement, which is just a change in position. Or is the total length of the path. Blah blah blah. So I'm just gonna skip ahead here and show us. So this first section of this booklet is about position versus and displacement, just as you were taught with Matthew. Although I think his book was a nice little bit. His ideas were nice and clearly labeled out. So position. Remember that position is just the location. So position, right? Position is the name for is your current location. Or a location, I guess, in more general terms, and it's often given some point of reference. Like your position might be, 30. So example, 30 kilometers north of the McDonald's, right? So if I live 30, well, that's a really crazy way to describe where I live, but I don't think I do, but maybe let's say I live 3 kilometers north of the McDonald's. So that gives you a position that tells me where I am. And then that reference point, the 3 kilometers north of McDonald's, that makes McDonald's what is known as the reference. So if it's the reference point, then it becomes the origin. So the origin is the position to which all other positions are referenced. Now, if we're talking about graphing, which we will be talking a lot about, then usually the origin is that 0, 0 point. So that point in a Cartesian plot, where you have this sort of thing that goes like this, and you have a thing that goes like this. This is called a Cartesian axis, and the origin is the reference point. All other points are referenced to the origin. And that point is 0, 0. And so it's the only point that has no values, and everything else has a value with respect to that point. Okay. So once you decide on an origin and come up with your endpoint, you can calculate the displacement. The displacement is the change in position between an origin and an endpoint. So maybe we should put a little definition for an endpoint. So let's put endpoint, the final position after some amount of travel. And I guess in this case we can call that displacement. And so the displacement is change at an endpoint. So for example, if in Laurie's example, which I guess was one we didn't read that was above, the origin was the town of Gladstone and her ending point was Winnipeg. By moving from one point to the other, she experienced a displacement of 150 kilometers. Put another way, at the end of her travels, she was 150 kilometers away from where she started. Now notice that in this displacement, I did not mention anything about how she drove there. Did she take any turns during that trip? Did she, did she actually take a straight line? Well, displacement always assumes a straight line, whereas distance is going to be a description that does not have a straight line. So displacement is represented by the symbol delta D, where the Greek symbol delta stands for change in, while the letter D refers to the position. Now in our class, I would actually like to take one step further, and if we are using the word displacement, I would like to put a little hat on this D, and that's going to be because in our class we're going to really refer to displacement as one where we know which direction it's gone. So that little arrow means direction, essentially. Oh, okay, well then, and you can see that that's what I talk about right here. As soon as you include a direction, you must use vector notation. And so in this direction, since Lori has traveled eastward to reach Winnipeg, her displacement is specified as 150 kilometers east of Winnipeg, or of Gladstone, right? So Gladstone is the 0, this is the origin, and this is her endpoint, Winnipeg. And so she is displaced exactly 150 kilometers east of her original position. Now, as soon as you have included a direction, you must use a vector notation, where an arrow is placed on top of the number or variable. Any measure that includes both a quantity or size and a direction is called a vector quantity. Another word for quantity or size is magnitude, which I like a lot. Magnitude. Like that. Okay? So displacement is a vector quantity. So we should really write this, and this is where this book needs a little bit of editing, is that these should be arrows on top of the D. All right, now the other definition that you sometimes will use, not in our physics class, but in other courses you might need to use, or in other aspects of your life, you might use the example of distance versus displacement. Distance usually does not include an arrow on it. So consider the following. You walk from your friend's house to back home. In the evening, how far is the distance that you walk? Well, distance is the total distance traveled. So the distance is 3 kilometers plus 3 kilometers, because each of your walks is 3 kilometers. 3 kilometers here, 3 kilometers back. So that gives us a total of 6 kilometers as your distance. But if you consider displacement, you start here, right? We said that this is the origin, and this point here, your house, is the end point. So the difference between the end point and the origin is 0. So you started at, your start at 0 kilometers, or you ended at 0 kilometers from home, because you're at home. And you subtracted from your initial position, which was 0 kilometers from home, because you were at home. And that gives you 0 kilometer displacement. Now this is the only time that you would include, you don't need to include a direction, because even though displacement is a vector and you should include a direction, you don't need a direction because you didn't go anywhere. So at the end of the day, you had a total displacement of 0 blocks from your home versus the total distance of 6 blocks. Notice that in 6 blocks, there's not sort of a descriptor of the direction that you traveled, because we don't talk about direction as much in distance. This is that the initial displacement is plus 3 blocks, and the displacement back is minus 3 blocks. So when you add up the total displacement, you'll also get to 0. So it is important to keep in mind the difference between distance and displacement. Distance refers to total movement in all directions. Displacement refers to the net movement from an origin. Moving farther and then returning closer to an origin results in a smaller net movement. So often there's a limitation here that the total distance or total displacement can never be larger in magnitude than the total distance traveled. It is more likely to be smaller in magnitude. So as in our example we just saw, there was a 6 kilometers of distance traveled, but there was 0 kilometers of displacement. All right, so let's look at this, this example here. So an object moves from point A to point B to point C, then back to point B along the line shown in the figure below. And so here's our line. I was wondering what they were talking about. So let's see. So it moves from point A to point B. So we're going to sort of start with an arrow here. We're going to put an arrow. So it moves from point A to point B. And then from point B to point C. So I'm going to move an arrow over here. So point B to point C. And then back to point B along the line shown below. And in this case, we're just going to raise up our arrow so that we can show them stacked on top of each other. Okay. Looks like I've got a little bit of an angle on that, but that's what happens. There we go. Okay, now I'm happy with it. All right, so this first displacement, right? So the first distance here, without thinking about values at all, we have a 5 kilometers from 0 to 5. Then 5 to 9, that would be another 4 kilometers. And then from 9 to 5, we would have another 4 kilometers. So without putting any directional notation on here, we have 3 values. We have 5 kilometers for our first distance, plus 4 kilometers, plus another 4 kilometers, which gives us a total distance of 13 kilometers. Now, if we needed to talk about the magnitude and direction, we would realize that this first one is in the positive direction because the numbers are getting bigger. The second movement from 5 to 9 would also be in the positive direction. But in the last step, let's break that down a little bit. Our origin point is at the 9 kilometers, right? And our end point is 5. And we always do end point minus origin point. So end minus origin would give us negative 4 kilometers. And here the negative and the positive work as our directional component. And so we end up with a positive movement and another positive movement, and then also one negative motion. And so the total displacement, adding all of these displacements together, so we can kind of say this is change in direction 1, change in direction 2, change in displacement 2, change in displacement 3. And the total is now only 5 kilometers. And it is positive. So now this is going to be our direction here. Direction. So if you're not writing north, east, south, west, or away or towards, then you can use the positive or negative, and that also serves as a directional component when we're giving that direction requirement for our vector. One other way to calculate this is to calculate this using the total displacement. So the total displacement would be finding the endpoint, right? Endpoint, and the origin, and just driving origin, and just drawing an arrow between the two of them. And then taking the difference between the endpoint, the end, which is 5 kilometers, positive 5 kilometers, minus the origin, which was the 0 kilometers. And that also comes out to positive 5 kilometers. So you can either add up each of the steps, each of the displacements individually, or we can take the difference between the end and the origin position. So let's look at the second example here. An object moves from point A to point B, C, and D along the rectangle shown below. So I believe they are saying that it's going to move in this direction, like this, A, B, C, D, and then back to A. Find the distance covered by the moving object. So point B, C, and D. Oh, it looks like it doesn't describe it moving once it gets to D. So I think actually I'm going to assume that it ends here. So we're going to say that it starts here. I'm going to use a different color than red so that we can see the difference here. And it's going to move from A to B. And then it's going to move in this direction from B to C. And then it's going to move in this direction from C to D. So starting at A and ending at D. So the total distance covered by the moving object would be 1, 2, 3, 4, 5. So we have 5 kilometers here. We have a total of 5 kilometers down this way. Or sorry, 3 kilometers that way. And then down along this side here, we have another 5 kilometers. Now, when we're doing displacement in 2 directions, it becomes a little bit different. But we're going to kind of be able to skip around a little bit in this first example. So we have 5 kilometers plus 3 kilometers plus 5 kilometers to give us a total to give our total distance equal to 13 kilometers. No direction included, right? Find the magnitude of the displacement of the object. Well, in this example, it gets a little bit confusing because we have some changes in direction that are north, south, east, west. But let's call this, let's go with like Cartesian coordinates on this example. So if we go Cartesian, then that makes this never eat soggy wieners, is what I always remember this. So north, east, south, west. So this becomes 4 kilometers east. This becomes 4 kilometers west. And this becomes 3 kilometers south. So when we think about the total displacement, one of the things that happens is we have a 5 kilometers to the east plus 5 kilometers to the west plus 3 kilometers to the south. Well, in terms of displacement, these two are equal and opposite because 5 kilometers east and 5 kilometers west are exactly opposite to each other. So those would be canceled out. So this is the same as saying only 3 kilometers south. And again, we could do this by drawing a final arrow. So we started at the A position and we end at D. So we could instead say that if we say that A is at 0, 0, it's our origin, then the only thing that we have is that D is in the same direction left and right, 0, but it is negative 3 kilometers to the south. So the change in direction is negative 3 kilometers, or let's go 3 kilometers south, minus the origin, minus 0 kilometers south, which equals a total displacement of 3 kilometers south. Or if you want to use numbers, you can do a negative 3 and all sorts of things. Okay, so for this question, it says an object moves along the grid through the points A, B, C, D, and E. And so we're going to give this a shot. And we're going to discuss this. I do think that I have done this question in the past, and I believe that if you make it go to F, it works out a little bit better. And I'm not sure why we wouldn't go to F if it was drawn here. So one thing to watch out is that in this example, every square is 0.5 kilometers. So for this distance here, this first distance, A to B, we are talking about only 1, 2, 3 kilometers here. So we've got 3 kilometers along the bottom here. We go up another 1 kilometer because it's only half each. 1 kilometer. And then we have 0.5, 1, and then 1.5. So this is going to be 1.5 kilometers in this direction. And then this example here will be 0.5 and another 0.5. So that gives us a total of 3 kilometers plus 1 kilometer plus 1.5 kilometers plus 0.5 kilometers plus 0.5 kilometers. So that gives our total 3, 4, 5, 6.5. 6.5 kilometers. Find the magnitude of the displacement of the object. So in this case, we are talking about moving from A to F, right? So in order to move from A to F, we have a couple of options here. The way we're gonna really talk about this is how much have we moved to the right, or in this case, let's call this east, and how much have we moved north, because we start here and we end up here at this F point. So we initially are moving. We actually can see that we can kind of see the result of this if we want. But one way to do this is to keep track of anything that's moving north and put those together, and anything that's moving east or west and keep those together. And a better way to do this is maybe even to think about this as positive. We are moving in the eastward direction. And then this way is moving away from east, right? So let's call that negative. And then let's call this one a positive east. So we have plus 3 kilometers east minus 1.5 kilometers east plus 0.5 kilometers. So that will give us a total, that's east. So we get a total for the east-west direction. We get a total of 2 kilometers east. And then there's also some movement up and down, right? We have a plus north. So we have plus 1 kilometer north plus 0.5 kilometers north. And that's this one right here. And so that gives us a plus 1.5 kilometers north. So we can say that the total displacement equals 2 kilometers east and 1.5 kilometers north. Now, there is another option, and that is for a more advanced option that we will be exploring later, and that's going to be using Pythagorean theorem, because if we are very astute here, we'll realize that we are moving actually here, and if we moved in these two directions, we would get the total displacement. And this is 2 kilometers and 1.5 kilometers, which tells us that this angled direction that we drew out here, this angle is actually forms a right angle triangle, and you can actually solve that solution with Pythagorean theorem as 2 squared plus 1.5 squared. Maybe you don't know, but a squared plus b squared equals c squared. So we could actually solve for this. This would be c on this side, and here's our a and our b. So we could solve for c. And in this case, this is actually one of the magic triangles. This side is always going to be only 2.5. So this is actually 2.5 kilometers. And so that would be 2.5 kilometers northeast. I only know that because it's one of the triangles that has a very simple solution. Okay, so we will get to this part later, but not right now, particularly in the next year in Physics 30. All right, so measuring displacement, there are several systems that can be used. We've already started to play around with the Cartesian system. That's north, south, east, and west. You could also generally refer to left, right, up, down, backwards, forwards. It doesn't matter as long as you have some direction indicated. On a number line, such as the one below, where each number represents a unit of distance, the displacement is referred to as a positive or a negative. Moving to the right on a line is a positive displacement, so we could have a positive displacement here. I don't know if you can see that because it's green on black, but whatever. Okay, that doesn't look that much better. So that's positive 2, right? Or positive 2, doesn't even have to have units yet. We'll get to units later. Or you could have a displacement in the negative direction, right? We could go negative like this, and if that's the case, then we would have negative 2 as our displacement. We move 2 units to the left. Moving upwards is positive, moving downwards is negative. We often will put in the Cartesian axis, and that Cartesian axis will give us the negatives and positives in both directions written out, and also tells you the sense of scale when you're using graphing paper, like the one below on the left here. So this is a nice graphing paper in a 1 unit graphing paper. Each square is 1 unit long by 1 unit tall. All right, so one thing we've been talking about right now is the concept of vector. That is something that has a direction. So think of all the quantities you are able to count and measure, and time it takes to walk to school, and the temperature outside on a hot day. The height of a tree. In physics, these are referred to as scalar quantities, quantities that possess a size or a magnitude that can be measured. So anything that has a size or magnitude that you can measure is considered a scalar quantity. This measurement does not have to be directional. Measuring time. So for example, measuring time, this is also a scalar quantity because it can be measured. 2 ways to measure it. You can measure it as an instant or as an interval. An instant of time is particularly a particular reading on a particular precise moment. For example, if you leave school at 8:15 a.m., that's an instant of time. It doesn't tell you how long. It doesn't tell you the length of a duration. It just tells you a specific time. In 60 seconds, I'm going to say this, right? So that's also an instant. Now, if on the other hand you want to measure the time it takes you to walk home, then that would become an interval. So intervals are going to be represented by that delta again for change. And so we're going to take two instants of time and take the difference to find an interval. The final instant and the initial instant, and that will become the interval of time. I've also seen this written as delta t is equal to tf minus ti. That's another instance. If sometimes we use 2 and 1, other times we do f and I. To illustrate, if you left school at 8:15, you arrived school at 8:30, then you would have walked for an interval of 15 minutes. 8:30 minus 8:15 gives us an interval of 15 minutes. All right, here's some interval questions we can practice and describe whether they're intervals or instants. You can pause here, do these in the booklet yourself, and then come back. Okay, welcome back. So a flight from Winnipeg to Toronto takes 1 hour and 51 minutes. Is that an instant or an interval? Sounds like an interval to me. It is a duration. Interval. A train arrives at 1:13. That would be the instant that arrives. You don't get any information about the duration. The next bus should be at 8:20. That's another instant. A phone conversation begins at 7 p.m. and ends 20 minutes later. So we know we can infer the interval here. And that's the last one. Scalars and vectors. Let's talk a little quickly about that. So scalars and vectors, when measuring quantities in science, we sometimes find it necessary to state the direction in which the quantities act. Most quantities we measure are scalars. So scalars are measured with a size or a magnitude, but without regard to direction. For example, temperature is a scalar. While it can be positive or negative, it does not have a direction like left, right, east, west associated with it. Time is another example of a scalar quantity. Time typically never goes negative anyways. We only think about intervals in the positive sense. So these they don't really have directions. They're always moving, but they're always moving in the same direction at the same speed. So they are considered scalar quantities. Your mass, you don't go on the scale one day and think about how much your scale has gone up or down. The movement of the needle or anything, you mostly are focused on the number. You're focused on the size or magnitude of the value. What is the actual number that you're measuring? Lengths can even be measured in magnitudes or radiuses, thickness of a pipe, for example. Those would all be sort of scalar values. Meanwhile, a vector would be quantities that have direction. So for example, force is a vector, and if they are vectors, they're going to have these little arrows on top. And I really, really need this book to be redone because obviously this should be F with a hat arrow there. Or displacement D should be D with a little arrow on top. You can pull on a door handle with a force of 25 newtons, or you can push against it with a force of 25 newtons. While these forces have the same magnitude, they act in different directions. So pushing against it, in this case, we might think that pushing with a force of, say, positive 25 newtons, and maybe we're pulling on it with a negative 25 newton force. So those would have directions. One force will open the door, the other will not. One force. Okay. Displacement is also a vector quantity because when you change your location, you change the direction that you're moving, or you move in a certain direction with that change of location. And from that position, from the point of displacement, we can move forward to another concept we're going to cover, which is velocity and versus speed. So speed is the sort of instantaneous magnitude of travel. So it describes how fast an object is moving regardless of the direction. The speedometer on your card measures your speed. It indicates how fast your car is moving, but it does not indicate the direction. For example, 100 kilometers per hour is legal speed for a car on the highway. It doesn't matter if it's 100 kilometers east or 100 kilometers west or 100 kilometers north, 100 kilometers south. That's not important. What is important is it's 100 kilometers. It's a magnitude, right? When we consider velocity, which is speed with direction, and again with the little hat on top, then that is a vector quantity. And that is going to be relative to a displacement and to a change in time. So it's really displacement over a time interval, and that means that it's going to have some direction. So you might have a velocity of 100 kilometers east per hour for 1 hour, and we'll end up where we end up 100 kilometers east. If we start at a point and travel 100 kilometers east for 1 hour, we'll end up 100 kilometers east of our original starting point. If we travel 100 kilometers west, starting from the same point, we'll end up 100 kilometers west of the starting point. These two velocities, 100 kilometers east and 100 kilometers west, are definitely different velocities. It is the difference in direction that makes them different. So scalars are quantities with size or magnitude only. This is the definition you need to know. And a vector is a quantity that has both a magnitude and direction. Okay, at this point, well, maybe I'm going to just finish up this last little bit since we already kind of discussed this anyways. So, introduction to displacement, time, and velocity. So, if we are going to be measuring the velocity, then we are going to be discussing a difference in displacement over an interval of time. So I'm going to just skip ahead. You can read all this stuff, but you've already covered this with Matthew. So remember, velocity equals a change in displacement over a time interval. So that's why it's going to be a vector, because displacement is a vector, and the vector property is transferable. Meanwhile, speed is a change in distance, or actually it's not even a change, it's a measure of a distance over a time interval. So in both cases they do use a time interval, but time's a scalar property. So when we mix the time and distance, we have a scalar with a scalar, and so the final value is speed, which is a scalar. In velocity, we have displacement and time, which is a vector and a scalar, and so that gives us a vector. Okay, so there's a little description here of the average, the equation for velocity, and I know there's a little bit of an error. There's supposed to be a sort of a division sign here, or the average displacement divided by a time interval. And we'll get that edited out one of these years. So what we're trying to say is that the average velocity, I'm just going to write it up here. So average velocity is equal to change in position or displacement divided by time interval, which is what we wrote above. So remember that the change can also be represented by the delta. Therefore, you could also write the equation as, and I'm going to rewrite this just because it doesn't look as nice as I would like it. So this is average down here is equal to the change in delta and displacement or position divided by the change by the time interval, which is a change in time. Okay, so let's write this problem out and see if we can figure it out. So think about what you've just read very carefully. Consider a race car driver in a race that covers 200 laps around a 1 kilometer circuit. So we've got a circuit that looks like this, and as it is 1 kilometer. And he's going to go around 200 times. Suppose the winner finishes the 200 kilometer race in 2.5 hours. What was their average speed and their average velocity? So speed, average, is simply the change in distance over the change in time. So in this case, we can say that the change in distance is equal to the 200 laps times the 1 kilometer. So that's 200 kilometers. And the time interval is the 2.5 hours. So for the speed, we get 200 kilometers divided by 2.5 hours. Let me think about that. 2.5 hours. So that's like... Well, oh, I got my calculator right here. Great. Okay, 200 divided by 2.5. I almost had it in my head. 80. Okay, so this gives us 80 kilometers per hour. All right, so that's a reasonable speed to do your race in. Now, if you do this as velocity, then you would be talking about the change in displacement over the interval. Well, in this case, the change in displacement, or change in position, is 0. They start and begin at the same spot. So now you have 0 divided by 2.5 hours. And so in this way, velocity makes it look like he did a whole lot of nothing, because you got 0 kilometers per hour as his average velocity. And that's because when he's going this way, he's got a negative velocity. When he's going this way, he's got a positive velocity. So over time, these values cancel out. Here you have a positive velocity. Here you have a negative velocity. So because he keeps going back and forth to the same spot, not back and forth, but all around, his total velocity averages out to 0. Okay, and so for the next section here, we have a little comment about uniform motion. So as long as an object continues to move in the same direction at the same speed, its motion is constant. You can say its motion is uniform. This will play very important in the concept of inertia that we're going to be covering very soon. You may notice that the symbol for velocity includes a subscript, average, or AVG, or average. That is because the velocity equation assumes an object is traveling at uniform motion. As you can imagine, it's easy for objects to change their velocity. Cars change velocity every time the driver presses down on the gas or brake pedal. So in this case, you would need to be more clear with how you calculate these changes. So next lesson, we're going to discuss some scenarios where the velocity is changing, but for now, we're going to focus on those uniform motions. So we're talking about the assumption that over a certain displacement, the velocity stays the same. And in this case, they're trying to show us the velocity calculated from the last time. So let's just pop in our little equation here. So they're saying that the velocity average, and they even forgot their symbols here. This is one thing that Matthew was not doing that this book has incorrect, is going to be 0 divided by 2.5, and so that's 0 kilometers divided by 2.5 hours, and that's why we got a total average velocity of 0 kilometers per hour. And that's one of the simplifications that happens when we talk about velocity. So if we use an average velocity equation, then we're going to be losing some information. We lose the information about how this car was turning around corners. We lose information about when the car was slowing down, when it was speeding up. It's also because we're talking about a time interval, not instants of time. You might discuss instants of time for the short term, but then when you zoom out to the bigger picture, which is what we're using velocity for really, is for discussing big picture ideas, like spaceships moving through space or planets rotating around the sun. In those cases, the velocity, the assumption of uniform velocity is probably pretty sufficient. We could assume, we can probably assume a fairly uniform velocity for how much the sun, our planet, moves around the sun, for example, because our planet doesn't really noticeably, in our lifetimes at least, speed up or slow down as it goes around the sun. And so this uniform motion is a good assumption in a lot of cases. It's a pretty good assumption if you're calculating, movements on a train, to assume that the train, if it's traveling for hours and hours and days on end, if we assume that it had uniform motion and we want to do some calculations about some of the physics of that train, then we could probably make those assumptions. If you're talking about short-term stuff like a sprint or short-term movements, then maybe uniform motion is not the right choice. Anyways, we'll get more into that and more into plotting out these changes over time in the following lesson review as we move our way quickly through the first half of this booklet.